quantum numbers and the four quantum numbers in the atom. So the first one is going to be the principal, second the angular momentum, third the magnetic quantum number, and the final one would be the electron spin quantum number. For the principal quantum number, is just represented by n. It is an integer starting from 1, 2, 3, and so on. This is going to tell us the size and the energy of the orbital. If we look at a periodic table, we can see that the first period is going to have 1 as the principal number. Second is going to have the number 2 as the principal number. So we have 2s and 2p. Both of them have 2 as a principal number. The third period is going to have 3 as the principal quantum number. So we have 3s, 3p. So 3 is a principal quantum number, but you have to remember that the d block, they do not start with 4. D block actually starts with 3. So this is 3d, 4d, 5d, and 6d. So this space right here, all these elements here in pink, are going to have 3 as the principal quantum number, just like these two in all of these here. Potassium and calcium are going to have 4 as the principal quantum number. All of these here are going to have 4 as the principal quantum number. And all of these here, up to krypton, are going to have the 4 as a principal quantum number. These two are going to have 5 as a principal quantum number, 4. So these ones on here are going to have the 5 as a principal quantum number, 5 as a principal quantum number, and so on. Another thing that you need to remember is F block is different. F block does not start with 6 as a continuation. Instead, it has 2 less. So instead of 6F, it's going to be 4F. Instead of 7, it's going to be 5F. So besides these as the 4 principal quantum number, all these elements are also going to have 4 as the principal quantum number. So it's just giving you the size and the energy. So let's practice. For P3, the number in front of P is going to tell you the principal quantum number. So this is going to be 4. Let me change it. 5F9, 5 as a principal quantum number. In between these two, 2P5 or 3P5, 3 is going to be larger. It's going to have the largest principal quantum number. The second quantum number is called the angular momentum quantum number, and this is represented by the cursive L. Let me change it over here as well. This is just telling you the shapes. We know we looked at 4 shapes before, S, P, D, and F. Don't worry about the G. We're just going to assign a number to each orbital or shape. So for the S, we're going to assign the 0, P1, D2, F3. If you forget it, how can you tell it? Well, you're going to start always with 0 and just going to continue being based on that n. So if your principal quantum number is 1, then your L needs to be between 0 and n minus 1. So in this case, it would be 0. If your principal quantum number was 2, your L would be from 0 to n minus 1, which is 1. If your principal quantum number is 3, your L would be 0, 1, and 2, n minus 1. So here's the principal and the L value for it. And where does it go in the periodic table? Well, if we look at n equals 1, we only have the S shape. If we look at n equals 2, we have the S and we have the P shape. So we have two letters here. If we look at 3, we have S, we have P, but also D counts as well. So it's telling us the shape that each principal quantum number holds. So these are the shapes I'm talking about. S has a spherical shape, P looks like a dumbbell, D looked like flowers, and F looked like more complicated flowers, at least to me. So practice P by looking at that table. P equals 1, 5, D, 9. The principal quantum number would be 5. The D is going to have a L value of 2 just by looking at that table. And what is the L value for F10? By looking at the letter F in our little table, F is going to have a value of 3. Third quantum number is called the magnetic quantum number, and this is represented by M little cursive L. Oops, sorry. So this, it could be, how can we determine the value of M of L? You look at your L. You look at your second quantum number magnetic, your second quantum number, the angular momentum, and this M of L is going to be all the numbers between negative L all the way to L, including the 0. So this is going to tell you the orientation of the shapes around the X, Y, and Z axis. So it's going to tell you the orientations here. We only have one orientation. Is a sphere in the center. So if we do our N, let's ignore the N for now. If we do L of S, so the S has a value of 0 according to our table. M of L are going to be the numbers between negative L and L. So this would be 0. If our shape is a P, it has an L value of 1. So our M of L is going to be all the numbers between negative 1, 0, and 1. If our shape was a D, it has the number 2 assigned to it. So M of L would be between negative 2, negative 1, 0, 1, and 2. And finally, if our shape was an F, it has a 3 assigned to it. So our M of L would be negative 3, negative 2, negative 1. We have to include the 0, 1, 2, and 3. What does all these numbers mean? Well, if we look at the letter S, which is the same as the 0L, it only has one orientation, and it is in the middle, just in the middle. If we look at letter P, has the number 1 assigned to it, has 3 different numbers. It means that these 3 have either an orientation around the x-axis, z-axis, or y-axis. So we have 3 different kinds of them. If we look at D, or number 2, L assigned to it, we have 1, 2, 3, 4, 5 different orientations around the axis. 1, 2, 3, 4, 5. And then if we look at F, or angular momentum of 3, we have 1, 2, 3, 4, 5, 6, 7 different orientations around the axis. So this is telling you the orientation of the orbital in space around the x, y, or z axis. Finally, let's do some examples first. So give a possible m value for 3p4. So p has a value of 1, of L value of 1. So m of L would be anything from -1 to 0 to 1. So you just have to choose from it. Give a possible set for NL and ML for 4D10. So we know the principal quantum number is 4. D, by looking at the little chart, D has a value of 2 assigned to it. In ML, you can choose between -2, -1, 0, 1, and 2. You could choose between any of this. Let's just choose 0 for now. This is a possible set. If you chose -2 would be fine. -1 would be fine. 1 or 2, they would be fine. Our last quantum number is the electron spin. So this is only telling you that the electrons are going to be placed opposite to each other in the offload diagram. So we start here with the 1s. You're going to place our first electron like this. The second electron will go like that. In the 2s, first electron will go like this, second would be opposite, and so on. Electrons, if they're together, they would repel each other. So this is just showing that they're opposite. They're going to try to be as far away as possible. And this is the MS, the electron spin. Now, Pauli's exclusion principle states that no two electrons can have the same set of 4 quantum numbers. So for every electron, you're going to have a different set.